Hi, my name is Guillaume Rochette, and I will present the paper Human Pose Manipulation and Novel View Synthesis using Differentiable Rendering. We present a new approach for synthesizing novel views of people in new poses. To do so, we'd start by disentangling the pose of a subject from their appearance. Rather than operating over mesh-based structures, our renderer uses diffuse Gaussian primitive that represent the skeletal structure of the human. Rendering these primitives results in a high-dimensional latent image, which is then transformed into an RGB image by a decoder network. Our novel differentiable renderer enables the synthesis of highly realistic images from any viewpoint and for any type of camera lens. The formulation gives rise to a fully differentiable framework that can be trained end-to-end. We train and evaluate our approach on two publicly available multi-view datasets, Panoptic Studio and Human 3.6M. We show how our approach can be used to synthesize humans in new poses from both scene and novel viewpoints, but also to allow motion transfer between individuals, as well as providing novel view synthesis from subjects captured from just a single camera. In the literature, traditional differentiable rendering pipelines try to align a smooth mesh with a highly non-convex image. This is problematic, as the more detailed the mesh, the better it can be aligned to represent the image. However, the more non-convex the optimization becomes, the harder it is to align. Such method requires strong regularization on the vertices of the mesh, as it requires the movement of the vertices to preserve local neighborhoods, as well as non-local constraint of what is inside and outside the mesh. On the other hand, neural radiant fields embed a representation of a scene given multiple images. Current methods are designed to render static scene or be limited in time, and such methods have difficulty generalizing to unseen poses, but not our approach. First, we localize the human joints in the three-dimensional space and simultaneously estimate the appearance of the body parts forming the skeleton. The appearance vectors are high-dimensional, and for visualization purposes we represented them using a color palette, as you can see in figures B and C. We transfer this information to a novel view and begin the synthesis process of the output image. Then we use our novel diffuse Gaussian primitive to move from sparse 3D joint location to a dense 2D feature image, using our differentiable density renderer. Finally, an encoder-decoder network then maps from the feature space into RGB images. We compute image reconstruction losses between the output image and the ground truth image in order to train our model. Let's dig a bit deeper and look at each step in turn. From the input image, our model encodes two modalities, the subject's pose and its appearance. Regarding the pose, we first infer the 2D pose from the input image using an off-the-shelf 2D detector, which is OpenPose. Note that this is the only part of the pipeline that is not trained. From this 2D pose, we use a 2D to 3D regressor, which is a small, fully connected neural network, in order to infer the 3D pose in the camera view relative to the root joint. We compute the root joint location in camera coordinates by finding the optimal depth, which minimizes the error between the reprojected 3D pose and the input 2D pose. Finally, using the camera's extrinsic parameter, we transfer the 3D pose to the target view. Now, in order to estimate the appearance of the subject, we look again at the input image and extract high-dimensional vectors for each limb of the skeleton. The extraction is done using a classic CNN backbone, namely ResNet50. Now that we have disentangled the pose from the appearance, we will move onto the rendering step. We aim to render a simplified skeletal structure made of diffuse primitives onto a dense high-dimensional feature image. The intuition underlying a new render is straightforward. Each primitive is an anisotropic Gaussian defined by its location and shape. A primitive is located at the midpoint between two connected joints, while its shape is defined to the direction between the two joints and scaled by the length of the bone. Using the camera intrinsic parameters and distortion coefficient, we tailor the rays passing through the pixels of the image to that camera. We measure the density diffused by each primitive along each ray of the image by calculating the integral of the diffusion along that ray. We know that objects closer to the camera should occlude those farther from it. Therefore, we handle the occlusions between primitives with a smooth aggregation step, in which each ray favors one primitive and discounts the other based on their proximity to the ray. It is worth noting that our renderer is differentiable with respect to each input parameter, as the rendering function is a composition of differentiable functions. The rendered image is feature-based and not photorealistic due to the small number of primitives. However, increasing the number of primitives would increase the computational costs and the difficulty in optimizing the overall problem. Therefore, we choose to enhance it in a subsequent step and view it as an image translation problem. We designed an encoder-decoder architecture which follows Stylian 2 style mixing and layer design principles. In order to recover high-frequency details, we incorporate the appearance estimated previously at each layer of the network. From the input image, we only estimate the information about the foreground, since it is impossible to infer background information that is not seen in the input image. Therefore, we use a segmentation mask around the subject to discard the background information from the target image. We assess the performance of the reconstruction by measuring the pixel-to-pixel distance between the image generated by the model and the target image in both pixel and perceptual spaces. To further enhance the realism of the synthesized images, we fine-tune our model with an adversarial framework using the classic GAN loss and the R1 regularizer. We also use an adversarial feature loss which complements the perceptual losses. Regarding the 3D pose, we require supervision to ensure that the location of body parts correspond to the pre-specified key points. Here, on the right-hand side, we can see the variation in the synthesis depending on the losses used during training. As we can see, simply using the pixel distance results in a blurry reconstruction, but adding perceptual losses greatly enhance the higher frequency details. The adversarial framework enables us to reach even finer levels of details in images. We have trained and evaluated our model on two publicly available datasets, namely Panoptic Studio and Human 3.6M. The Panoptic Studio dataset provides markerless multi-view sequences with great diversity in subjects' clothing, morphology, and ethnicity. There are 31 HD cameras recording at 30 fps. We restrict ourselves to single-person sequences, which leaves us with a total of 37 subjects. This results in roughly 100 million image pairs for training and evaluation. Regarding Human 3.6M, there are 4 HD cameras recording 7 subjects, which yields about 8 million pairs of images. On the right side, we can see the results on both datasets. We notice a sharp gap in performance between models trained on Panoptic Studio and Human 3.6M, which we attribute to the granularity of the skeletal model. Indeed, on Panoptic Studio, the skeletal model provides detailed information about the hands and face, while on Human 3.6M, the skeleton is limited to the body, and the face and hands are represented by a single point. This video shows how we can perform novel view synthesis of known subjects in previously unseen poses using Panoptic Studio data. From the input image on the left, we extract the pose and appearance before rendering the primitives in the novel viewpoint and producing the synthesized image which resembles the target image on the right. This process mimics what happens during training. As we can see, our approach is able to handle large view changes while preserving fine-grained details such as the fingers or the folding of the cloth. This video shows how, given an input image of a known subject in an unknown pose, we are able to synthesize novel views for unseen viewpoints. In this case, we create a fictitious camera, which is virtually orbiting around the subject, viewing them from previously unseen angles. This video shows how to perform motion transfer between two humans. From the image in the top left corner, we extract the pose of a previously unseen subject. At the same time, we extract the appearance of a known subject, as seen on the top right corner, and we synthesize the combination of these two into a normal view, as seen on the bottom right. The bottom left image simply shows the similarity in terms of pose in the normal view. Notice how the visual appearance of the second subject is preserved while the pose remains faithful to the first subject. To conclude our presentation, we have introduced a new mathematical framework enabling the synthesis of humans from novel viewpoints. Our method explicitly disentangles the human pose from its appearance. It also enables the motion transfer and synthesis of unseen pose from non-existing viewpoints. Its modular design gives us the possibility to replace each component individually with better ones in the future. Our model is entirely parallel and therefore open to real-time application. Thank you for watching this presentation.